Hi everyone. In this video, we take another look at orthogonal vectors in an inner product space. We're going to discuss some examples where we compute orthogonal complements of sets of vectors in an inner product space. So recall that if V is a vector space with an inner product as indicated, so V is an inner product space, we say that two vectors x and y in V are orthogonal if their inner product is 0. And this is denoted by this symbol, x perp y. Suppose S is a set of vectors from the inner product space, then we define the orthogonal complement of S to be the set consisting of all vectors x in V such that the inner product of x with every element in S is 0. So in other words, S perp or the orthogonal complement of S is the set of vectors which are perpendicular to all vectors in S. So here's an example. Suppose V is the inner product space R2 with the standard inner product or just the dot product. Consider a vector V in R2 with components both non-zero. Then the orthogonal complement of V is the set containing V perp. By definition, it's the set of all two vectors, say xy, whose standard inner product with AB with V is 0. But by definition, this is the set of all vectors xy such that ax plus by equals 0. So it's the set of all points satisfying this equation. So this can be written as the set of all two vectors where x is arbitrary and the second component y is equal to negative ax plus b. That is obtained from this equation. So we're talking about the span of the two vector with components 1, negative a over b. And this can be expressed as the span of the two vector negative b over a. Note that the vector AB, as given, determines a line in R2. And that line has slope given by b over a. Our computation shows that the elements in span of 1, negative a over b are vectors that satisfy this equation, ax plus by equals 0. And that equation defines a line in R2 with slope negative a over b. In other words, the orthogonal complement of V is the line that is perpendicular to the line determined by the vector AB. So to illustrate, suppose this is vector with components AB, then we computed that its orthogonal complement is the span of the vector negative b over a. And the span of negative b over a is the line containing that vector. And that line is perpendicular to the line determined by vector AB. Note that with the standard inner product, the y-axis, so that's the line x equals 0, is the orthogonal complement of the x-axis, or the line y equals 0. And conversely, the x-axis is the orthogonal complement of the y-axis. So with the standard inner product in R2, the notion of orthogonality is just the usual notion of being of perpendicular vectors or perpendicular lines. Here's another example in R3. So suppose R3 is endowed with the standard inner product. Consider the set of vectors in R3 with 0 x component. So the second and y components, the second and third components are arbitrary. So if you think of R3 as the XYZ space, then this set S is just the YZ plane. Then we compute the orthogonal complement of S. By definition, it's the set of all vectors ABC whose inner product with all the vectors in S is 0. But all the vectors in S are of the form 0YZ. So we want to find all vectors ABC such that the dot product of ABC with 0YZ is 0 for all Y and all Z. By definition of the dot product, so this expression is equal to, or can be written as, by plus cz equals 0. So we want to find all vectors ABC such that the y, or rather the second and third components, B and C respectively, satisfy by plus cz equals 0 for all real numbers y and all real numbers z. But because y and z are arbitrary, so we want this to be satisfied for all real numbers y and z. The only values for B and C for which this entire statement is true is where both B and C are 0. Okay. So in other words, S-perp, the orthogonal complement of S, is the set of all vectors in R3 whose second and third components are 0. And first component is arbitrary. But this set of vectors is nothing but the x-axis. So here's a picture of that situation. Okay, S. So here, this line is the x-axis. This is the y-axis. This is the z-axis. The YZ plane is this purple plane. So this is our set S in this example, and we computed that S-perp is the set of all vectors with 0 y and z components. So that is this line. Okay. So this line is the orthogonal complement of the YZ plane. And conversely, the YZ plane is the orthogonal complement of the x-axis.